SwayamPrabha. Digital India. Educated India.
Hello all. From this video we'll start discussing about the micromechanics of lamina. As we already mentioned, micromechanics is when we look into the details of the lamina which composes of the fiber and the matrix material. So the idea here is, if we have or know the properties of the fibers and the properties of the matrix material, can we use this data to predict what is the properties of the lamina? So we start with the objective of this micromechanics of composites, where we say we are looking for the relation between the composite and constituent properties. Most often these are only fiber and the matrix, but of course there are other composites where you have more than two constituents. Maybe there are some nanofillers as well as micro-sized fillers. So but here we are trying to make it general, saying that it's just a relation between the composite and the constituent properties. These constituents, as I mentioned, can be two or more. So let's see, if we find this relation, what is it we can answer? So the kind of questions we are looking at is, so here this is the modulus of the fiber and the Poisson ratio of the fiber. So let's say that we know the properties of the fiber, and then we also know Vf. In a while we'll define what is Vf, but as of now it is the proportion of fibers, and similarly here Vm is the proportion of matrix material. So it's the volume ratio of fibers to the total volume of composite, and here it is volume of the matrix material with the volume of the total composite. And let's say we also know what are the elastic properties of the matrix, the Young's modulus E and the Poisson ratio M. So with all this information at hand, can we now predict what are the properties of the composite is what we are looking at. Most often we use this to predict the stiffness of the lamina. Stiffness meaning we are looking at the E1, like the stiffness along the fibers, E2 stiffness perpendicular to the fibers. We also look at this Poisson ratio mu12 and the shear modulus G1. But in addition to this, the micromechanics can also be used to predict the strengths. Then instead of looking at the elastic properties of E or Poisson ratio, there we'll be looking at what is the failure strength in tension and compression for the fiber and the matrix materials, and we will also look at loading either along the fiber or perpendicular to the fiber. But once we know these strengths, how can we use it to predict the strengths of the lamina, like the X meaning the strength of the lamina along the X direction, strength of the lamina along the Y direction, and the shear strength of the lamina. So these are what one can do with micromechanics once we know the details or the properties of the constituent materials. So the questions we are addressing here are, first we are seeing how stiffness or strength of the composites varies as we vary the proportions of the fibers. So let's say, for example, we have a glass fiber reinforced composite, meaning we have glass as the fiber material, and let's say the matrix material is epoxy. So if I pick glass and epoxy, I still have options to choose what is the proportion of the epoxy and what is the proportion of the glass. As we increase the proportion of the fiber content, the properties improve, and as we decrease the volume fraction of these fibers, the mechanical properties are less. The simple reason being the matrix properties are not as superior as the fiber properties. So that's what we will be looking at, how the stiffness and strength vary when we change the proportions. Or the same question can be looked in a different fashion, saying that now what is the proportions I need to come up with such that I achieve a target strength or stiffness. Now as you can see, this is the same question but put in a different way. the moment we see this, now it becomes a question about material design. The reason is now we are designing a material for a target value of either stiffness or the strength. Once we say that for a particular application, let's say I need a stiffness of, let's say, 200 gigapascals. So now my first thing I have to do is I need to choose what is the matrix material and what is the fiber material. Let's say I have chosen either glass or carbon as the fiber and epoxy as the matrix. Just by choosing these materials is not enough. We have to choose these materials and then design the material, meaning I need to come up with the right proportion such that I meet my target stiffness. For example, I was saying 200 gigapascals. So this is what we meant by material design. So these are all the possibilities one can do once we know or understand the micromechanics of composites. So there are two approaches to get to these relations. So as we mentioned, we are looking for these relations, and then there are two approaches. One is the mechanics of materials approach, where we use simplifying assumptions. So we make assumptions like how the materials deform. We also make assumptions about how the load is shared between these constant materials, and because of these assumptions, the analysis become simple. But there is another approach called the elasticity approach, where we do a more rigorous satisfaction of physical laws. What are these physical laws? These could be equilibrium equations, compatibility equations, or the relations between the stress and strain. So the only difference between both these approach is, in the first approach we make more assumptions to make the analysis simple. But in the second approach, we make less of the assumptions and rely on the physical laws like I just mentioned, the equilibrium equations, geometric compatibility, and stress strain relations to solve the problem in a more exact and a more rigorous fashion. So both approaches are possible. This being an introductory course, we'll focus more on the first approach, which is the mechanics of materials approach. Okay. So before we move forward, let's first see what are the assumptions we made when we start looking at the micromechanics of composites. Most often we look into the linear elastic regions, meaning we are looking that the matrix as well as the fiber materials are linear, because as we already mentioned, we are looking at composites which are linear elastic. Of course, as an advanced topic, one also can look at the non-linearities or non-elastic behaviors, but for a initial discussion or as an introductory course concepts we need, let's focus on these linear elastic behaviors. So now let's start with the lamina level and see what are the assumptions we are making. First, we said it is a linear elastic material. This is a possible assumption if your loads are small, relatively small, and your strains are also small. If you are looking at small strains, usually the stress strain relations are linear. But of course, as we increase the strains, that's when the relations become nonlinear. And we also are assuming that we consider these lamina as microscopically homogeneous. So meaning there is no variation in the fraction or the volume fraction of fibers from one part of the lamina to the other part. In all parts of the lamina, we are saying it has equal contributions of fiber and the matrix. And we are also saying that this material is orthotropic. This I think we have already looked in detail, like what materials we call it as orthotropic, meaning the properties are different in different directions. Especially when we come to lamina, we say these properties are different along the fibers and perpendicular to the fibers. Okay, so these are just the assumptions for the lamina, but we also have assumptions for the constant materials, starting with the fiber. So fiber, we said, is a homogeneous material. We are also considering it as an isotropic material, meaning the properties are the same in all the directions. And lastly, we also say that it is linear elastic. So as I mentioned, since we are looking at small strains and small loads, relatively small strains and loads, I think we can still go with the linear elastic behavior for most materials. We are also mentioning these fibers are regularly spaced, meaning there are it's again to do with the homogeneous distribution in the lamina. And lastly, we said that all these fibers are perfectly aligned. So if we are looking at a unidimensional lamina, meaning that all the fibers are all in the same direction, now we say we consider that all fibers are, let's say, 0 degrees, meaning they are perfectly aligned along this axis, x-axis, for example. And then we don't account for any small distribution, because in reality it's not like all fibers are in the same direction. There is a small variations, maybe a few degrees here and there. And the second assumption we make is they are perfectly bonded to the matrix material. This is an important assumption to be made, because in reality it's not always true that we have a perfect bond between a fiber and a matrix. Like all materials have defects. Similarly, in composites, one of the major defect people come across is improper bonding between the fiber and the matrix. So what we mean is, it's not as though like there is no bonding at all, but at some instances or some places there are some voids occurring between the matrix and the fiber, and because of these voids there is no perfect bond. And in addition to voids, there could be many other ways where this bonding could be imperfect. But for this micromechanics approach, we are saying that we'll assume that it is perfect and develop equations based on those assumptions. Now we move to the assumptions for the matrix material. Again, we say it is homogeneous, isotropic, and linear elastic, just as what we assumed with the fibers. And here we also assume that it is void free. In reality, matrix materials like epoxies, they do have voids coming from preparation, the way we manufacture these composites. But we are assuming that there are no voids, meaning the contribution of these voids to the properties of the composites are not so significant. So we are ignoring this for a moment and assuming it to be void. So these are the major assumptions we make even before we go and derive those expressions for between the composites and the constituent materials. Okay. So now we come to a very important concept for this micromechanics, where we discuss about the representative volume element, which we also call it as RVE. R standing for representative, V for volume, and E for element. So what we see here, let's say, is a lamina with lots of fibers and surrounding matrix material. So we are saying that it is a macroscopically homogeneous lamina. So if we want to really predict the properties of these lamina using the constant properties of the fiber and the matrix, it is not possible or feasible to apply it to the whole lamina as such. But instead what we do is we focus on a small area. Let's say this red dotted lines is the small area we are looking at. This smallest region of the material that has the correct proportion. This is again very important, saying that this area what we are choosing should have the correct proportion of fibers and matrix. So for example, let's say we are working with a lamina which has a volume fraction of fibers of, let's say, 60%. So which means the fibers take 60% of the volume and the rest 40% is taken by the matrix. So the same thing should be followed even at the RVE level. So this red dotted line is what we are calling it as RVE, and what we are saying is it should have the same proportions, meaning it should also have the volume fraction of the fibers as 60%. So now let's see that this is the RVE which we are focusing on. which is microscopically heterogeneous. Why are we calling it as heterogeneous? Because we now acknowledge that there is a fiber as well as a matrix, the representative volume. I hope this is clear. Let me emphasize saying that when we look at this small region, we need to ensure that we capture the right proportions of the lamina in the RVE as well. Okay. So once we are able to come up with this RVE, usually what happens is there is only one fiber in most of the RVEs, but there are instances when you will be forced to take more than one fiber. For example, let's say we are looking at bidirectional composites where we know these fibers are in two perpendicular directions, and since these are woven, there is a three dimensionality into it. They are not perfectly straight, but instead these fibers need to climb up and down the perpendicular fibers. In those situations you may have to take two or more fibers, but at least in this lecture what we are focusing on is two dimensional, but the moment you go to three dimensional you will be coming across those situations. Okay. Now we look at a very fundamental concept which we need to understand for working with the micromechanics, which is to define what is the relative volume as well as the relative weight, and see if there is any relation between these two, relative volume and relative weight. So now let's start with the volume fraction, which we are defining with V. Actually, in the last one or two slides, we have already seen this, and we have in fact defined what it is. We are defined the volume fraction, the subscript F refers to fiber, and the subscript M refers to matrix. So here the small v's correspond to the volume fraction and the capital V's correspond to the actual volume. So for example, capital VF is the volume of fiber in the composite, and Vm of course is the volume of matrix, and Vc, what we refer is the volume of composite, which has both the fiber and the matrix. So as we can see, it is self explanatory, saying that the volume fraction of fibers is volume of fibers by volume of the composite. Similarly, volume fraction of matrix is volume of matrix by volume of composite. Similar to this, okay. From this understanding, we can also say the volume of the fibers plus the volume of the matrix gives you the total volume of the composite. And if taking this expression and if you divide it by the volume of the composite on both sides, what we get is something like this, right? Vf by Vc plus Vm by Vc equals 1. And if we replace these ratios with the volume fractions, now what we get is a relation between the volume fraction of the fibers plus volume fraction of the matrix material, which goes to 1. Here we have assumed that there are only two constants, which are the fiber and the matrix, but if there are more than two constants, then it should be summation of all the volume fractions should go to 1, where I can go from 1 to n. N is the number of constituents in the composite we are considering. Okay. Now that we have looked at the volume fraction, now let's look at the weight fraction. So weight fraction we can define in the similar lines. The small w is for the fraction and the capital W is for the actual weight. So here the capital WF is weight of fiber, capital W's matrix M is weight of matrix, WC is weight of composite. Okay. And then we can now define these ratios or the fractions as uh, weight of the fiber by weight of the composite, and Wm is the weight of matrix by weight of composite. And similarly, we can also show this relation between these two weight fractions, as we can start from saying that the total weight of composite is just the sum of the fiber weight and the matrix weight. And if we divide the equation by the weight of the composite, we come with this expression which says the sum of the weight fractions of the fiber and the matrix is unit. And again, of course, we can generalize this for n number of constituents and simply say the Wi summation is 1. Okay. But now let's see, the weight can also be defined in a different term, where we say weight is a product of density rho times the volume, right? So this we know from a very school level physics, where we say rho here is the density times the volume gives the weight of the material. So once we use that expression, now I can replace this Wf with density times the volume, and similarly the weight of the matrix material I can now replace with density of the matrix times volume of the matrix, and similarly the weight of the composite is the density of the composite times the volume of the composite. And in this expression, if we divide by volume of the composite, then we end up with this expression which relates both the densities as well as the volume fraction. This kind of expression is usually called as the rule of mixture. Later, when we discuss about micromechanics for stiffness prediction, we'll come across this rule of mixture again and we'll discuss more about it later. So now let's summarize what we have discussed in this video. So this is an introductory video for micromechanics of lamina. So where we said we are trying to find the relation between the constituent properties, which are fiber properties and matrix properties, to the composite properties. We said there are two approaches, which are the mechanics of material approach and the elasticity approach. The first one is based on more simplified assumptions, and therefore the analysis is simple. Whereas in elasticity, we do apply a rigorous application of physical laws to get an exact solution, and which is more accurate, but it is a bit tedious. Later, we also discussed about the assumptions we make at the laminar level as well as the constituent levels. So we made several assumptions. Mostly we said these are homogeneous materials, both the fiber and the matrix. They are isotropic and linear elastic materials. We also made assumptions that they are perfectly bonded and perfectly aligned. We also mentioned about these void-free matrix materials. Some of these assumptions uh, are not exactly true, but we do go with the assumptions because it makes our analysis simple, and these later we'll see the expressions are not too far from the experiments. Later we discussed about a very important concept for micromechanics, which is the RVE, or the representative volume. We said this is the smallest area which represents the exact proportions in the lamina. The reason why we are focusing on a small area is then we can go into the exact representation of stresses and strains within this element. And finally, we looked at defining what is a volume fraction and what is a weight fraction. But we also said, depending on the number of constituents, the summation of the volume fraction is unit, where I can go from 1 to n. Similarly, for the weight fraction, also we said the sum of all the weight fractions is 1, where I going to 1 to n number of constituents. Later, we introduced density as well and showed how we can relate density with the volume fractions. With this, we conclude this video. In the next video, we'll be looking at how to apply the micromechanics to stiffness predictions in a lamina.